Thank you very much for having me here and those organizers for this really nice workshop. Yeah, so I'm going to talk about PageRank centralities. We saw in some of the talks here, but not very much. So if you go to computer science conference, then much more talks will be about centralities. So Google PageRank, probably most of you know that what Brin and Page have introduced in '99. It was one of big factors of success of Google. So the paper that they wrote about PageRank was had a very ambitious title, Bringing Order to the Web. And actually that was what it was, because before that people tried to rank search results by text matching, which is of course very cruel. Like for example, if you want to find something about, say, Dutch railways, and you type in Dutch railways, then you are more likely, if you look at the text match, you're more likely to find some blog of some traveler than the site of the Dutch railways, because maybe the official site will not even have these words in the title. So, so that's why it's not really even user-friendly, the text match, and they wanted to do something else. And what they did was very simple, and actually the idea was not, strictly speaking, even new. I mean, they invented it, but similar centrality measures actually were already used in sociology before. Only this application was such a fantastic, such a huge scale. So what is a PageRank? So here we have a set of web pages, say from 1 to n, and Ri is the PageRank of page I. Okay, and then it consists of two components. So here is a summation over all pages j that have a link to I. Okay. And what we have here is PageRank of page j, right? And then we have this coefficient alpha, which originally was set to this magic number 0.85. So we have coefficient alpha at this summation, and this score Rj is sort of equally divided between all the pages to which page j points in. So that's why it's divided by the out degree of j, yeah? And so this is coefficient alpha, and complementary 1 minus alpha, and here we can put this qi, and qi is just, you can see it as a probability, so you can see q is a probability measure, and originally, like in the very basic form for PageRank, qi is just 1 over n. So this, you can see the system of linear equations, and in this talk we will see it as a system of linear equation, but of course it's much easier to understand it with a random walk interpretation, and that is a very famous easily bored surfer model. So when you look at these equations, what we see is if you can interpret this Ri as a stationary distribution of a random walk. So what the surfer does, when the surfer is page j, then the surfer throws a die, and with probability, or a coin, with probability alpha, the surfer decides, I'm going to continue following the links, and picks one of the outgoing links at random. So that is the additional probability 1 over dj, where dj is out degree. And with probability 1 minus alpha, the surfer says, okay, now I'm bored, and I just pick a random page from the distribution Q. And that was the random walk. So the only thing that is not very precise here, in that sense, so this is a system of linear equation that you can interpret as random walk, except in the web there are a lot of pages with no outgoing links. And those are, of course, not a part of this equation. And those, of course, you have to, if you want random walk interpretation, then you have to decide what do you do with those. So the standard solution to this is to say, if you are at a page with no outgoing links, then you again use distribution Q for random jump. But then you can imagine that for proper balance equation for Markov chain, I need here then an additional term. What do I do when I'm at a page with no links? But it is very easy to show that so it is very easy to show that the solution of this equation will be exactly the same as if you make a random jump from this dangling nodes from the pages with no links only up to a constant, up to a normalizing factor. So basically, if you renormalize it, then you will obtain this stationary distribution. So that's why it really doesn't matter. But it's very good to have this random walk interpretation in mind just for interpretation of PageRank. Okay, so that is some addition if you want to use this Markov chain interpretation. But the bottom line is that when my page I is important, it is important when many important pages are pointing to it. Many is important because then I have a big summation here. And it's also important to get links from good pages because then you have this score high. So, and that was what makes it work. And of course, you could just rank by in degree, but that's very easy to spam. I mean, you can create a robot that creates a lot of false pages that point all to your page, and you can boost your in degrees very easily, as much as you want. Except if Google figures it out, they will punish you severely. But this sort of wild boosting of PageRank was actually taking place in huge scale on the web. So PageRank is slightly more difficult to cheat because you also need important links. Okay, so this is the model, and no, it's not used for search anymore. So that people in mathematics, when they present about PageRank, say, yeah, this is what is used for web search. It was, and it was one of important factors in success of Google because that none of us goes beyond first page. That is like that. There was a lot of research about it. Most of the web surfers, when you do web search, mostly you never go beyond first page. So it's extremely important what is on the first page. And PageRank was doing a great job, much better than say TextMatch. But now they do some sort of link analysis, but precise form of PageRank they don't do anymore. They do something a little bit else. They're extremely secretive about what they exactly do. If you ask them, they don't tell you. A commercial secret. But we know that what you know from your own experience, they do, for example, a lot of personalization. Like, for example, I work at the University of Twente, but there is also a football club, Twente, which is arguably more famous than the university. But if I search Twente, then most probably I will get university as my first hit, given my search and web viewing history. Because I don't ever look anything about football and very often do something related to academics. So similarly, your location plays a lot of role. So for example, if you are based in, say, Eindhoven and you type something like house renovation, then you will get the firms that do it in Eindhoven or in the Netherlands, but not those who do it in the UK, for example. So location is also very important. So it's, yeah. But PageRank turned out to be an extremely useful mechanism for network analysis because it's a global characteristic of the network, and it apparently it says a lot. So it's used for many different purposes, and here is just some references. So spam detection, for example, you can do by giving really low Q score for spam pages. You immediately make it very small importance, and then that will affect everybody the spam page links to. So for example, that is one of the tricks that you can do. You can do it for link prediction, personalized PageRank especially. You can use it for clustering by discovering the neighborhood this way, and things like that. So you can do Wikipedia ranking. My co-authors did it, but there is also MIT project going on that. So you can do a lot of really interesting things. Okay, so that's why PageRank is still very interesting to study. And it is not easy because it's a global characteristic of the graph. And that's more or less the reason for the long journey that Remco quickly, shortly described to you. So this is the question that I was thinking about for the last many years. If we know something about the structure of the graph, what can we say about PageRank? So about PageRank distribution. And that is not very trivial because of this global characteristic of the graph. Okay, so I will quickly explain to you how this thing is computed, because you can imagine that's probably the biggest Markov chain in the world. Nowadays, web pages, I think 100 billion will be a modest underestimation, the size of the web. So they solve it by matrix iteration. So we can write this system of equation in a matrix form that I think I don't need to explain for this audience. And yeah, for matrix chain interpretation, you will have slightly different matrix form. And as I said, the solution will be basically the same up to the norm. And then what you do is just, you just solve it by matrix iteration. So this equation is not difficult to solve. You have immediately the solution. What is difficult is inversing a 100 billion by 100 billion matrix, even when it's sparse. So that's why nobody does that. So what is used is series expansion. So what they actually do is power iterations. So it's very standard. So they start with some initial vector and then start substituting the previous iteration to the right-hand side. And then after iteration k, this is what you get. And what you see here is this sum is forming up to this sum. So that is, here you're going to get the right answer. And this one is going to vanish exponentially fast because of the alpha between 0 and 1. And that will be important for the stock. So that's why, and that was important in practice because this is how the whole thing is actually computed. I must say that when the PageRank was invented in '99, there was a huge amount of work on PageRank computations actually. That question is more or less closed in 2005. Matrix is very sparse. Power iteration methods are extremely efficient, and basically even with such a huge matrix, there is no problem to do power iteration. So it's, unless something else happens, like that's not really scientifically very important challenge anymore. But there was a lot of work which allowed actually to come to that stage when it's not a problem anymore. So it's not naive power iteration what is done. Some linear algebra tricks are used to, or some methods are used to make it faster. All right, but what I was thinking about also is this, and this is actually the important picture. So we all know about scale-free behavior, Power law in graphs, and this is a paper, you can see the captions, but this is from this paper, preprint in 2002, then they published, I think, in 2004. This is the scale-free behavior of in degree of a network, and this is the scale-free behavior of PageRank scores. And you can see that these are the same, or maybe up to constant, right? It's log-log scale, so maybe up to a shift, but you see exactly the same power law exponent. And the question is why? And of course, you can say, of course, PageRank is summation over in degree, so in degree must have a huge influence on it. But if you look at linear equation, it's not precise. I mean, maybe mean field, that's true, but it's not precisely true. Like, why? We have another source of high PageRank, that's a PageRank of other nodes. So it is not very clear how to explain that mathematically. And this is basically the question that I was thinking about. So I think it's sort of a good style in this conference to say something about Nature paper. So that was a paper by Goshalom Barabasi in Nature Communications. And actually, I agree with the first part. There is very little that we know about relation between PageRank and network topology. What I don't completely agree is that there is a lot of money in it. I mean, if you take my experience, you cannot, there is not so much money in PageRank research, but maybe, I don't know, but it's actually, it's a puzzling question. So what they did in this paper is something a little bit else. So basically they showed the difference in the robustness of PageRank in scale-free versus no scale-free networks. But that's sort of obvious, definitely for computer scientists, because if you have very large nodes, then of course they will have large PageRank just because of their large in degree. So it's not terribly surprising to me. But they had some elegant explanation for that. So that, yeah, it didn't give me more understanding, basically. Okay, so how we decide to approach this is through stochastic model. So here is your original model for PageRank. And we don't know how the solution of this equation behaves. But then what we thought, okay, maybe we can approach it this way. So this is an equation, and why don't we just replace it by stochastic equation? So PageRank of a node, let it be just random node. Let's just take one node, and that its PageRank will be by all means a random variable, right? Then this random variable will depend on its random in degree, so we have to sum, right? And it will depend on it will depend on random page rank of its neighbors, right? And these neighbors will also have random out degree, and there is random, this personalization factor, this jump in probability Q. And by the way, here in this equation we scale everything, because this is a stationary distribution, so average page rank is 1 over n, so it goes to 0. So if you scale it with n, then it will have an average of 1, so that is more convenient. So we scale everything, and this is the equation. And now we are in a very good setting, because for this equation we can analyze this equation and we can learn how the solution behaves. So and this is what we did some years ago. That's in a little bit more convenient form. And with my PhD students some years ago, we did exactly that. So we look at this recursion, and then indeed we could prove that if in degree has a power law, in this case regularly varying, but this is the most important part. If in degree has a power law, then page rank also has a power law. And even the constant, this up to coefficient, and even this coefficient we can compute explicitly. So this was very nice, and actually this recursion is very interesting, and my co-author Mariana Alvear-Creviotti did a lot of nice work about analyzing this recursion. So if you want to know anything about this recursion, check her papers. They have done a lot. So now this recursion is very well studied. However, there is a lot of cheating going on, because to analyze this recursion we have to make assumptions about it. So the assumptions that we made, particularly, for example, that these RJs are independent, right? And if you make these assumptions, then immediately you sort of impose a branching structure on your network. Because if you think that, okay, I have a node and there are in degrees, and all branches, so page rank of all the nodes, that depends on everything else, are independent, it means there are different separate branches. So immediately you impose a branching structure. But we all know that, that random graphs are not necessarily trees. So and then the question was then how can we extend it to random graphs? And that is exactly what we did. So I will tell you a little bit what we did. So we basically constructed a directed configuration model. And in this directed configuration model, we introduced extended by degree sequence. So this is in degrees, out degrees, the coefficients in the equation, and the personalization, that is plus q. So that we give to every node, and then we need to make some assumptions. So the assumptions are in the spirit of law of large numbers. We need some things to converge. In particular, we need second moment of out degree to be finite. But that's not terribly big restriction, because out degree is something that web page creates itself. So typically out degree are not so wildly varying as in degrees. So if we had to assume finite second moment of in degree, that would be a pity. But finite moment of out degree is okay, a second moment. So, and then also we assume these typical regularity conditions that you can also find in Remco's book, that when you consider configuration model, then you want empirical probabilities converge to something. So that we also assume. And directed configuration model is just your configuration model. Basically, you have here outgoing stubs and ingoing stubs of this is the same vertex, and then you connect them at random. So here we created directed edge from V1 to Vn, and that you continue and then you get the graph. And then once we have a graph structure, then we can formulate the question very cleanly. So we introduced this matrix that used to be matrix P in the page rank. So basically, we just write down the page rank equation in this matrix form, and what we are interested in is this page rank vector, and even more specifically, we are interested in the distribution of the first coordinate of this vector. Because first coordinate, because no, without laws of generality, we can simply consider node number 1, right? So what we want to know, if this is the solution of this equation, where the matrix is generated by directed configuration model, what is then the distribution of the first coordinate? So that's the equation. And we will do it by coupling with branching process. And you know what happens when you do coupling with branching process. When you follow a link, then of course you get a size bias distribution on the other side. That's why we introduced two distributions, and actually this distribution with a star is actually the distribution of the properties of original node that you randomly choose, and the one without star is a size-biased one, and it's size-biased by out degree, because when we explore from a node towards, so we explore incoming links of a node, then we are more likely to pick guys with larger out degree, and that's why it is size biased by out degree. That's why it's more likely, larger your out degree, more likely you are to be in that tree. And then this is our main result, and I have put here 2016 because last week it was accepted to random structures and algorithms, so I was very happy about it. But actually we proved that, of course, you don't get accepted in one day to this journal, so the result is 2014-15, something like that. So this is the main result. So you recognize the stochastic recursion. That is exactly the one that we had originally, only now I put all these calligraphic letters. So basically, because now the stochastic recursion consists of limiting distributions. So this is a stochastic recursion, and it consists of limiting distribution for size-biased version without the star. And where our PageRank actually converges, it converges to a linear combination of solutions of the stochastic recursions, where this n is sampled from size-biased version, and this n0 is sampled from not size-biased version. So basically, you take a random vertex, then you have its in degree, it's distributed as n0, and the distribution of PageRank in the limit, as n goes to infinity, will be a linear combination of solutions of that equation. So yeah, so this is the main result. I hope that is clear. How much time do I have?
9 minutes.
9 minutes. Okay, great. So then I can say something about the proof. Actually, I think a similar style Vincent was given in his proof. So we have 3 steps, and each step uses different methodology. So what we need to do first is to show how fast our PageRank actually converges in matrix iterations. And that is the first step. And surprisingly, it's very easy when I show you, but surprisingly, it took us some time because we have to a little bit change the mindset here. Coupling with the tree is something that's probably familiar for people who studied, for example, distances in random graphs. So this is also we do. So we want to see how close is our configuration model to a directed tree. And finally, in all our constructions, we have used empirical distributions. So the last step is to show that this empirical distribution version will converge actually to the limiting distribution version. So that will be the last step. So I will show you a little bit how it works. So matrix iterations, this is for the first step. So we want to know how fast our PageRank is approximated. And then, so you basically you do the matrix iteration, and it's quite straightforward to obtain this. So when you look, what is the difference between my limiting PageRank and PageRank after k iterations? And k iterations means that the paths of length k contribute into your PageRank, but the k+1 neighborhood not yet. It's very easy to write this inequality. That is just straightforward. But we have this factor n, and that is very annoying. It is very nice converging if it is alpha to the power k, but this factor k, this factor n is very annoying. And we tried to use the results, general results on convergence of Markov chain mixing times, and see what is the difference, because this is basically a stationary distribution, and this is the k approximation of it. So for that we do have good evaluations, but it doesn't help, because all these results about exponential convergence, so they will give us this term, but the coefficient will depend on the properties of the chain, and in particular we can get rid of this n. But luckily we could, for a slightly weaker statement, we could do it using just Markov inequality. So we said, okay, actually what we need is the probability that this guy, so the limiting and and the approximation is not very big, right? But that is just Markov inequality, and since the norm is just summation of the norms, then this is just 1 over n, the total norm, and that's how we get rid of the factor n, and that was really convenient. So that was the first step, and after that we could prove actually that say the probability is vanishing. So if your k is logarithmic, say, then this will be always vanishing. So for any logarithmic k, this will be vanishing. So the xn goes to infinity, but as slow as you want. So that was very good. So basically, the bottom line is PageRank converges after finite number of iterations, more or less, for all purposes. And the next one, the next one was coupling with branching tree, and that is also a little bit different for directed networks, because what we have is what we call a thorny branching tree. Because if we exploit, we start from this node and we go to see who contributes in its PageRank. So we go to explore by incoming links. But all these guys have also outgoing links. And we also have to keep this bookkeeping of these outgoing links that we have already seen. So we label them all, and we try to count how many are them. So because we want to detect this sort of scenario where at some point we encounter a node here and it has incoming link, which actually was that outgoing link that we already have seen. At that point, our tree is not a tree anymore. This is where coupling breaks. And we prove the coupling lemma. And the coupling, so the store number is the number of the generation when the coupling breaks. And for all purposes, this mu parameter should be greater than 1. So actually, this case is the most interesting. And basically, this result says that so for this, the interesting scenario, this coupling breaks after logarithmic number of generations. That's something what you would expect. We do need this finite second moment of out degrees for that. Otherwise, the branching process will not have finite average, and it will become a mess. And of course, the main technique is that branching processes behave like their averages, but you need to prove concentration and things. You need to control the maximum number of offspring. But this is more what you usually see. So that I will skip. And finally, we say, okay, our graph looks like a tree, great. Now we compute everything on a tree, but we use empirical distribution. And there is some technical difficulty, but let me show this. So we need some additional assumption, but basically, this last step can be done based off this recent result of my co-author. So that was basically after some technical puzzling that was almost directly applied. So I'll skip that step. I rather show the numerical results. So the theoretical approximation does quite well. So here, this red is the theoretical approximation. And this blue is the actual PageRank after, say, the limiting. So when you compute it exactly, and we see that even up to small curvatures, the lines are the same, and it converges also very fast. So basically, the result is already very good for 10,000 nodes. And 10,000 nodes is nothing. You know, I was in program committee of a computer science conference, and the track chairs wrote precisely the following: any experiments on the World Wide Web data with less than 100 million pages should not be considered seriously. Yes, but when we get mathematical results, we are very happy to run our MATLAB code and show that it works for, say, 10,000 nodes, and then we are happy. But actually, 10,000 nodes is a very small network. So I'm actually quite happy that it converges for such a small network already, because real networks are much bigger, so it means our approximations will be very good. And finally, this will be the last one. We also compare to the Wikipedia, and that's a puzzle. And that's a puzzle that I'm busy with now, because here's green is the theoretical, this complementary distribution function, this one. So it's 1 minus distribution function. And this the distribution, as we predict, of PageRank scores. And by the way, we predict the whole distribution, not only tail. So and red is the English Wikipedia, and this distribution is very similar. And it should not be, because Wikipedia has a lot of triangles, and which we sort of ignore in our configuration model. What we did for configuration model, we took the degrees of Wikipedia, reshuffled them, made the configuration model out of it, and then computed PageRank on it. And it was too similar. So getting rid of all the cycles, triangles, whatever not, randomly rewiring Wikipedia, we get the same distribution of PageRank scores. You have to also realize the distribution, right? So it's not like the same pages receive the same score, but the distribution is very similar. And that's a puzzle. So now I'm trying to see how triangles actually affect PageRank, and that's also not very easy, but yeah, maybe some preliminary results we have, and actually they do affect. So, but exactly quantifying it is not so easy. So that's all I wanted to say today. Thank you very much.
Are there any questions? Yes, Svante.
Yeah, so you said repeatedly that the PageRank course depends a lot on the in degree, but it is not only on the in degree.
Yes.
So have you tried to look at the joint distribution of PageRank and in degree and see how much dependency there is?
Yes, we did. So, and actually this is exactly, it's a very good question, and for that there is exactly an answer. So I have even a paper where we computed, but in that branching settings, the dependence between the in degree and PageRank. So basically, a fraction of pages have high PageRank because of rich neighbors, and a fraction of pages will have high PageRank because of their high in degree. So that is, of course, and that's logical, because if your neighbor has a big PageRank and not very large out degree, well, out degrees basically don't play a role. This division by out degree does play a role. So then it gives you a big chunk of this probability mass, and it will have the same tail, basically. So a finite fraction of nodes become rich and have high PageRank because of their rich neighbors and not because of high in degree. And we can quantify it quite precisely.
Yeah. I was wondering, have you also thought of, or is there a relation between this and the so-called responder-driven sampling, where you try to infiltrate in hidden populations? So.
Yeah, not that I directly see. So this, I mean, in this work, I think, okay, it is for the first time that we characterize completely PageRank on a random graph. But I don't see the direct connection that you mentioned. But maybe we can discuss in a break, because PageRank is related to a lot of things, because it's related to distances, it's related, I think, to epidemic spread, because it's like just weighted sum of your paths, more or less, and you can do a lot of interpretations with it.
Okay, let's
Yes.
thank Nelly once more.
Thank you very much.